Yeah, okay. And that is a difficulty because it doesn't want to move.
Okay, that's fine.
There we go. Righto.
Will it go forward for you? Yeah.
There we go. Righto. Whoops, that's the end. Okay, I'll start again. This is several examples of the use of duplex stainless steel there, and I'm going to be talking about introducing it. Gary Coates will be talking on the 26th of June in part 2 about this, and he'll pick up the bits I've missed and put some other stuff in as well. So that's an aide-memoire. So when molten stainless steel comes together, the atoms go into a square and eventually, or a cube rather, and eventually settle into that body-centered cubic. Then people add nickel to it, and nickel is a different size, and it means that the atoms don't fit into the middle, and so they suddenly go into a face-centered cubic. All the atoms are sitting around on the faces of this cube. That's fine. If you add enough nickel, that happens. But if you don't add quite enough, then instead of going from the ferritic stage straight to an austenitic stage, you wind up in the middle with a duplex. And a duplex, instead of adding 8% nickel, you've added about 5% nickel or other variants of it. Or you can add manganese, nitrogen, copper, and so on. And you get this alloy, which is stronger than both the ferritic and the austenitic, and behaves a bit like the austenitic in terms of cold work strengthening. And interestingly, if you're looking at slurry resistance, then it's about 3 times better than 316, but we'll get to that sort of thing. The ferritic austenitic colours in this micro here, this is basically a cut section that's been polished and then etched because of the 2 phases. Here we have the green is the background ferritic, that is what it solidified as, and the white or sort of green, slightly greenish colour is the austenite, which has grown out of that as it cools down. The black specks are what we don't want because that's saying that there's something wrong with the metallurgy, but we'll come back to talking about this and how the metallurgy develops and go from there. So what's actually in there? We've got chromium, we've got molybdenum, we've got nitrogen. Those give you your corrosion resistance. And you've got somewhere between 10.5% and 30% chromium, up to about 7% molybdenum, although there aren't many alloys around, it just makes it a bit hard to weld. And you've got nitrogen, nice, free, easy to put in nitrogen, which does good things for the corrosion resistance. Then you've got the mechanical properties, and the things that control that are the nickel, the manganese, and again, the nitrogen. And the amount of material, well, nickel can go up to 37%, although it doesn't do anything like that in the duplex stainless steels. Manganese up to about 11%, although most of the stainless steels, the duplexes, don't have as much as that, they have a lot less. But this nitrogen bit is really quite important, and it actually is of critical importance to making sure that stainless steels, the duplex stainless steels, work. So there is a piece of stainless steel. It's sitting in the middle of its chromium oxide film, and all stainless steels have that chromium oxide film. It's the basic thing. Doesn't matter whether it's duplex, doesn't matter whether it's austenitic or ferritic or whatever. It's all this film of chromium oxide around the outside that actually means that it's corrosion resistant. Unfortunately, this one's had a particle of steel embedded in it. And so that steel, if it gets wet, will corrode. That will release ions, which are positive. If there are chlorides around, they get attracted towards it. And so you wind up effectively with a ferric chloride solution around that spot, and you'll get a little rust spot. You'll get a micrometer deep pit, which isn't anything to worry about, except you're worried about having a nice bright piece of stainless steel. So you get rid of it. How do you get rid of it? Well, use chemicals, because if you abrade it and polish it, then all you're really going to do is smear the steel that's left on the surface there, and you get a bigger smear. How good is the corrosion resistance of duplexes and in fact all stainless steels? This pitting resistance equivalent formula has been around for 40 years or so, and it's for saying that look at the chromium composition, add up 3.3 times the molybdenum plus half by 3.3 of the tungsten if it's been added, and then add 16% of nitrogen. Remember I said that nitrogen is actually very important for duplex stainless steels, and here is part of the reason. So the higher that number is, the better the corrosion resistance. Ferritics, well, this doesn't dissolve very well in ferritics, so usually that term is omitted, but for the duplexes, we leave it in. And you've heard probably of super duplex or super austenitics, and all that means is that those particular materials, if they're called super, have got a PRE that's greater than 40. And if you put them into seawater at ambient temperatures, and a bit of a furry number ambient, but let's say at mid-20s, then it won't corrode. Nickel is not in that equation. Nickel is important, but it doesn't affect the corrosion initiation, so it does not appear in this. Nickel is all about the structure and how it responds to mechanical, or the strength is one of the things. This pitting resistance equivalent is an empirical approximation, and it's designed to compare grades, but it correlates really quite well with the thing called the critical pitting temperature and the critical crevice temperature, CPT and CCT, which is the temperature required to cause either pitting attack or crevice attack in a specified test solution. It's not looking at what happens in the real world. It's looking at, here we are in a test solution, what has actually happened. And here is a little example. This is looking at CPT, critical pitting temperature, versus the PRE. And as you can see, it's pretty much a straight line. And we've got super austenitic up there, we've got a super duplex there, we've got an ordinary duplex there, and a bundle of austenitics down here, and even, oh yes, there's another duplex there, 2304. So 2304, 2205, and 2507, all duplex stainlesses. The three exceptions for this, and you'll wonder why they're there, these alloys over here are much better corrosion resistance, but that's because they've got a lot of silicon in them, which does unfortunate things to their ductility, but it does improve their corrosion resistance. There are also some interesting things that the Japanese claim, where they put 100 parts per million of tin into a ferritic stainless steel, and they said, wow, we've got marvelous things here. And then they tried to persuade people to buy it, but it was going to cost a lot more. So how much corrosion resistance do you get if you're looking by PRE, what for the different materials? Well, martensitic, these are the things that you make blades out of. Precipitation hardening, these are the things used in aerospace and defense. And they start out very low in terms of corrosion resistance and don't go up a long way, actually, but they've got lots of strength. The 300 series go from, well, let's think, you can get down to about 16, I suppose. Yeah, up to super levels. So a wide range of corrosion resistance. The 200 series start lower because there's less chromium in some of them and stop on the way up. The ferritics go very low. This is absolutely the lowest, the 10.5% chromium of the ferritics, up to super ferritics. And the duplexes can go even further because they put a whole lot of nitrogen, a whole lot of chromium, and a fair bit of molybdenum too, and they get very, very good corrosion resistance. So this gives you an idea of the range of corrosion resistance that you'll get with a duplex and with various other of the alloys. No numbers on it because then you'd wind up getting absolutely bored. That's looking at PRE. This is looking at a bundle of different alloys, austenitics and then duplexes, for critical pitting temperature and critical crevice temperature, and it's done in a test solution, in ferric chloride solution, G48. And as you can see, as you might expect, they're labelled wrong. This is an embarrassing moment because this has been used. Okay, let's just look at the fact that the whole range is steadily increasing as you go up in levels of chromium and moly and nitrogen and the corrosion resistance. And there's differences between the CPT and the CCT. Oops. It's an acidic, very high chloride oxidizing environment. It is not a service environment. So getting a number from there wouldn't be enough that you could go and say, yep, we'll put it into this service environment. Stress corrosion cracking. This is Sandvik data, where we're looking at the 304 and 316, which really won't cope with very much in the way of chlorides. 50 degrees C and a few parts per million, and you can get cracking. Duplex distinctly more. We're up at what, 140 degrees, and super duplex is up even more. And these are regularly used at quite high temperatures and get no in seawater. And just from the point of view, that's seawater there. So let's have a look at why people think duplex stainless steels are cost effective. And there are some good properties, higher strength than both the ferritic and the austenitics. The ductility is less than the austenitics, but greater than the ferritics. Yeah, that's perhaps a problem, but usually not. Chloride stress corrosion cracking, very much better than the austenitics, less than the ferritics, which basically don't suffer from it. Unfortunately, because it's a duplex, it's got ferrite and austenite in it, and so it will embrittle with hydrogen. More corrosion, high corrosion resistance to organic and mild phosphoric acid, and it'll unfortunately embrittles at low temperatures. Actually, you can get some quite low temperatures, but you've got to be careful about it because it's the ferritic phase in that actually embrittles. And the reason I put sorry, I missed the slide. Phosphoric acid is the mildly reducing one that it's quite good against. Good formability for the strength, but again, the duplexes, high and low temperatures, it doesn't cope with too well. Mind you, 300C or 270C is not too bad, but we'll come back to that. Good weldability, it's different from the austenitics, but not quite as easy, but you can still weld it reasonably well. It's a learning curve for both fabricators and welders. Erosion corrosion resistance better than the austenitic and ferritic. I think you saw the note I put up earlier saying it's about 3 times better than the 316. It is sensitive to unwanted phases that happen if you're welding or you're doing a lot of heat treatment. And it's generally going to have a lower price for equivalent corrosion resistance. The reason for that is because it doesn't have lots of nickel in it. And the only little snag is that it's a bit harder to process out of the mill. And so there isn't quite the wide availability of it. It's growing, but it's still not enormous. It's still, you know, less than 5%. ASTM and Euronorm both have it in. And let's look at 3 different grades, the 2304, the ordinary duplex and the super duplex. So a low duplex, and compare strengths. Yeah, not very different. And you really wouldn't expect it to be different. It's just the way these standards treat the materials. The tensile strength's about the same. Tensile strength of the 2507, again, about the same. Ductility, it's all in the 20 to 25, except for the ASTM version of the elongation in 2%. Sorry, this is elongation in 2 inches percent, and this is just the A5 arrangement. And for compositions, EN is typically a bit narrower than ASTM, although there's not a lot in it. Just a couple of mechanical things. Put 2 millimeter sheet and you're trying to bend it 45 degrees. And here we've got the curves so that you read off what you actually are aiming for and what you've got to actually bend it to. Okay, and it's different for 316, 2304, 2205. And if we had 2507 in there, just think about where that would be, because looking at it, you've got to bend the 316 about 50 degrees, the 2304 and the 2205, you've got to go about 62 degrees. So would the line for the 2507 be below or above? And of course you immediately say, oh, it's got to be below because it's stronger. And so it needs more bending. I should have used that as a poll. In terms of a bend radius, 3 or 4T. Looking at mild heating, and I'm talking about 300 degrees, it's the thing that you're supposed not to do with duplexes because warm heating up above that temperature gets you up into a potential problem of embrittlement, but it's at 300 degrees, you should be reasonably safe. So look at 300 degrees from 25, 4316, and you get about a 42% drop off. For 2304, same range, about 35%. And for the super duplex, you get again about 35%. So it is worth heating up a bit, but don't go beyond 300. And in fact, if you're talking about TUV, then don't go beyond about 270 because there is a potential problem once you get up to 475. I'll come back to that. Looking at thermal expansion, just other bits and pieces. Okay, where's our austenitics? Here up at 16.5 compared to 11 for ferritic stainless steels or 12 for mild steel. And duplex is sitting down nearer to the mild steel. So in fact, if you can deal with the thermal expansion of mild steel, then you can deal with the thermal expansion of duplex. Whereas if you're dealing with austenitics, then you've got to be a lot more careful. So if somebody can weld with austenitics and not have distortion problems, then duplex shouldn't be a problem for them. There are just other problems. Yeah. And Charpy impact. This is data for 2707, 2507, 2205 and 2304. So going from hyper to super to ordinary or standard to low. And yes, you can see that down at -40, well, starts dropping off at about -20 or so, but you can get well down. And really it's a matter of how much ferrite you've got in there. The requirements here, 45 joule at -46C, so that's right down there. Or for Arctic service, -200 joule at -100. Yeah, you're not actually going to get there, are you? Because 200 joule is up here. And the austenitics, well, you can go right down to absolute zero. Upper temperature limits. ASME says don't go beyond 315. That's because of the 475 degree embrittlement. TUV says 300 for lean duplex down to 250 for the welded standard grades and for any of the welded super grades. So, yeah, there are some specific limits for, well, the solidification range is just numbers. Scaling temperature in air, that's basically the chromium. Sigma phase formation, about the same, although it goes up a bit further for the super duplexes because they're higher alloy. And the nitride carbide precipitation, bit lower band, but both starting at about 450. And this 475 degree embrittlement, that's right slap bang in that range. Although you look at the curves and you think, gee, 300 is being conservative, but hey, that's what engineers are all about. So what makes ferrite tend to form? Chromium, molybdenum, and silicon. Remember I said that silicon doesn't get added a lot. I'm not talking about the 4%, I'm talking about less than that, but still, it is an issue. It is a feature, and it used to be in the DeLong diagram for welding consumables. Austenitic, well, the nickel, obviously, the nitrogen, obviously, carbon, but the trouble is if you start adding carbon, you wind up with the problem that you had with 200 series, that you get carbides, and so it's very hard to weld. And manganese. Now, one of the things about manganese is you put lots of manganese in and suddenly it becomes easier to dissolve nitrogen. So therefore, putting manganese in gives you 2 for 1. You get a small effect of going towards the nickel process and a larger effect about putting nitrogen in. Other factors, silicon can also give you additional corrosion protection, but that's nothing to do with the ferrite austenite. That's just to do with a film formed on the surface. And if you remember those 3 high silicon materials on the CPT curve, then that's the reason why they're over there. Impurities such as sulfur and phosphorus are low in the duplex and are not usually a corrosion issue. They're not, you don't add, say, sulfur to make a free machining duplex. You do other things. It's a two-phase structure, intermediate levels of nickel, somewhere between those. It's got some advantages and some disadvantages, but one of the major ones is this intermetallic phases that occur with the high chromium and high moly stages. So that's the super duplex and the hyper duplex. You can get this with ordinary duplex, but you've got to work hard at putting too much heat into it. Some properties are different from either the ferritic and the austenitic. I'm not going to go into that in detail. The 5 families, the lean, well, the ones we know about, the standard one, the 2205. Then there's the 2304, 2507 or 0 and 100, and then a hyper. And I'm going to talk about these in detail towards the end. The family, just a bit of history, started back, if you're talking about the austenitics, the ferritics and the martensitics, 1910 to 1919, I'm sorry. And that included making stainless steel knives. Duplex family was first discovered in Europe and then commercialized in the late 1920s as 329. Came as cast products for pumps and then as a wrought material. This is a picture of the first known picture, which Gary found from somewhere, 1932. And they would have had to anneal at 1000 degrees C after welding because they weren't able to control the carbon and the nitrogen in that, and they actually weren't able to reliably put it in. So while they were used in the 40s to the 60s, it was as castings, except as castings and bar, and it was used as castings and bar, but not as welded product. Not good ductility and lower corrosion resistance because you couldn't get a decent balance between ferrite and austenite, and that's quite important. Okay, why is it important? Well, let's just look at the straight austenite forming things, but leave out the carbon and leave out the nitrogen because they're not metals and they're quite hard to control. So then the austenite ferrite ratio is going to be determined by the temperature in this phase diagram. So for this level of nickel and these levels of chromium and so on, here you'd be an austenite, there you'd be ferrite, and there you'd be duplex. You'd have some of each. And this curve, this phase diagram goes like that. So it's melting, it's all liquid, and then it starts to solidify. And by the time it's solidified there, it's in the ferritic range and it's all ferrite. And it cools down to about 1000 degrees or so. And then you've got some of the ferrite going to austenite. And as you keep going down, it keeps on changing. And down there gets to about 50% and 50%, and it doesn't change any longer because it's sitting at about 1000 degrees C at that point. And from there on, it's solid. So any change that's happening from there is going to be by solid state diffusion. And that's not fast. It definitely isn't fast. Okay, so remember, this is just simply what happens with the austenite formers and the ferrite formers that are metals, not the carbon and the nitrogen. So that's a phase diagram. It's showing equilibrium conditions, and the change from ferrite to austenite takes some time. If the cooling of the metal down to about 1000 is too quick, then there'll be a lot of ferrite. That can happen during welding, of course. The molten weld pool can cool quite quickly, especially if you're welding something thin, and you end up with nearly 100% ferrite at the weld. That's not good. You can't get, because of the composition, you can't get too high austenite, although if you welded with nitrogen and the shielding gas, then yeah, that'd raise the austenite levels quite significantly. Okay, so in the 1970s, the phase imbalance was fully understood, and the and is really critical, argon oxygen decarburization, the AOD that everybody uses now, plant has designed and was being taken up by everybody. Was that the fastest changeover anyone imagined? So the impurity content could be controlled, and you got decent control of the ferrite formers. That led to controlled additions of nitrogen, and so nitrogen is now in all duplex grades, absolutely all of them. Increases the speed of the ferrite to austenite transformation, so you don't have to be quite so bothered about how quickly it's cooling down above 1,000. And also the nitrogen, it's an austenizer itself, saw it in that, so the nickel content can go down, which is good because nickel's expensive. Decreases the rate of formation of intermetallic phases, increases the corrosion resistance, that's that by 16 in the PRE formula, increases the strength, you saw that on that first chart. It's nice and inexpensive, it's plentiful, it's easy to use. And the only problem is you can't go beyond about 0.6%, but still, that's not much, and it's good and helpful. Of course, only a very small amount is that, as I've said, just 0.6. The higher nitrogen alloys are a bit more difficult to hot work, and because of the 475 embrittlement, you shouldn't really go warm forming. And I said, well, okay, up to 300, maybe you could. This is just another way of saying that nitrogen is great stuff, but it's going to add one extra bit, and there's the weld, and that's the rolling, the structure. Nitrogen, the shielding gas, if you're using TIG, will give you a bit more austenite there. If you put too much in, then you'll get very much austenite, and it'll fail you. It'll fail all sorts of things. If you put it in the purge backing gas, then it's going to give an improvement in the corrosion resistance to the root run. But in Europe, people use Formia gas, which is a mixture of nitrogen and hydrogen, which reduces the heat tint, and the hydrogen doesn't enter into the arc because that's a backing gas. Two pictures. This is wet impure phosphoric acid. This is super duplex. Here is a desalination plant. This is super duplex pipe. The only welding in this is where the flanges go together. Sorry, where the flanges are welded to the pipe. And that's in Australia. And I did a lot of work in that plant. PRE. There are alloys with a lot lower PRE because the PRE for the super duplex is up around 40. 26. Better corrosion resistant 316, and it's lighter because it's stronger. Lots of palm oil. I like this place. I've been and visited it back before they had this. But there's gates, 6 ton of 2205, 24 ton of carbon steel, plus obviously some cathodic protection, to close the gates at high tide, open them from mid tide and scour out the silt. Because it was getting so people could just walk there all the time. Really wouldn't do. The monks didn't like that at all. Middle East, this is Doha, duplex with a low reflectivity and a PRE of about 30. Heat, humidity, salty air, sand, all collect salt. And compare that to Singapore. The race course has got the galloping horses roof. Tokyo has got ferritic roof, both with PREs in the mid-20s. And it's simply climate. And this is lean duplex applications. You go from pressure vessels, tanks, lighting, bridges, and assorted structures. And here's a list of all the sorts of things that lean duplexes can be used for, because they're not as expensive, because they don't have so much metal in them, but they've got high strength and quite reasonable corrosion resistance. We'll come back to that. And you can select either the lean or the standard level, or even the super grade if you need to, if you're going into seawater. Okay, a bit about metallurgy. You can get the intermetallics, sigma phase, chi, lavs, etc. Don't worry about what they are. It means that they're intermetallics, so the things that should be giving you corrosion resistance are tied up with each other, so they don't make the chromium oxide film. The other snag is that you can get nitrides, carbides, not so much if you've got impurities around, but there's not an awful lot of carbon in the duplex stainless steels. But if you've beat it for a long enough time, yes. And all of those mean that the corrosion resistance goes down, the ductility and toughness change. So here's time at temperature from welding. So this is 1 minute, that's 0.1 of a minute. And here is a curve where the start of sigma phase happens in 2507. Here's the curve which we've got for sigma for 2205, there for 2304, and you can see quite clearly as the alloy goes down, the problem goes down. Nitride, I'll talk about that later. Alpha prime, this is down here looking at about, well, it's centered at, actually it's a bit above 475. Oh, that's F, sorry, 475 over here. These curves here are having lost 50% of the hardness or 50% of the toughness, but it takes 12 minutes for that and 100 minutes for losing the toughness. So it's a lot slower than particularly the sigma phase formation. And it happens for all of the alloys. These are all duplexes, 2304, 2001, 2205, 2550, etc., etc. And all of them have this double curve arrangement, and all of them, the ones that are right up at the far end here, are the ones that go quickest. But this is in seconds or in hours down here. Upper arcs, intermetallics, lower arcs, the ferrite change, the alpha to alpha prime. Higher alloys, you have more rapid formation. Carbides, I've said carbides really aren't usually an issue. So this is beating you over the head with it, but if you go down too fast, if you cool really, really fast and work at it hard, then you just don't get any austenite, too much ferrite, and so you lose the benefits of having a duplex. If you take it very slowly, then you go down through the the sigma phase and through there. And so very high heat input would do that, or really high interpass temperatures, and you'll get the intermetallics there and you'll lose some toughness down there. And really, this is the sweet spot. You go down, you miss the nose there, but remember that this is really quite quick. So if you have repairs, that's a problem, because the time we're talking about along here is cumulative. If you make a mistake and have to repair it, wow, that's a problem. And this is an example. This is, remember the picture we saw before? This is just a black and white of it, obviously, but here we've got the ferrite, here we've got the austenite, and nothing in the way of nasty bits and pieces. Here we've got a lot of them, lots of duplex. And it probably in this case occurred because the interpass temperature was above the 150 to 250 C for prolonged periods. So you just wound up with too long in the higher temperatures. This is some work that I did back, oh God, 30 years ago, I suppose. It was 0 and 100, and it deliberately induced about 20% sigma in this. So that's the austenite, and the brown is really pretty dark because it's very, very sigmatized. It was so sigmatized that one of the samples we broke just shattered like a piece of glass. It's quite amazing. So then you run it through an induction heater and get it up, and suddenly you're down to, well, we measured it, we could measure about 0.3% sigma in this. There's some rubbish sitting on the surface as well. Why did that happen? Well, this was the thing that caused it. This was a piece of pipe work, and it was made out of 0 and 100, and their welding was pretty awful, and they had some repairs. In fact, they had 2 goes at repairing it. And then they found that after it had been in service for 9 months or so, they started leaking about that distance from the actual weld, and it's just sigma phase. They took some of that pipe, or rather they took some of the pipe that was left over that hadn't been done like that, and did an annealing process on it, and that's it. So it really looks quite nice. So we've got the slow cooling problem, intermetallics, and over here we've got chromium nitrides. Sorry, yes, slow cooling. Over here we've got too fast. So we've got no austenite, and we've got lots of ferrite, and the nitrogen can't dissolve in it, and so it forms into nitrides. And I'll explain why that's bad in a minute. In fact, I'll do it right now. Imagine you've got an arc strike, and it wasn't in the weld, or it wasn't on a starter tab. So it's splat cooled on the large heatsink of the welded item, and it splat cools and becomes ferrite because it cools down till it's too low for the austenite to nucleate and grow. And at that point, all the nitrogen trapped in the liquid ferrite is no longer soluble. It's got no austenite available to diffuse to, and so it precipitates out as chromium nitride. And that is bad. Typically, experimental work showed that you get large grains of ferrite and then traces of austenite on the grain boundaries, and beside the austenite, the ferrite is free of nitrides. But beyond that, the ferrite is absolutely loaded with chromium nitrides, and the surrounding zone around those nitrides is depleted in chromium. Oh dear, we're relying on the chromium to give yourselves a corrosion resistance, and it's locked up with nitrides. And in fact, chromium 2 nitrogen, 2 chromium atoms, so about 7.4 times the mass of chromium is removed compared to the nitrogen. And in addition, chromium nitride is pretty big, so it's slow to diffuse, so the corrodable zone with low chromium remains with lower PRE. And this work found that you had to grind almost 1 millimeter depth underneath your splat to actually get to the bottom. And how do I know that? Because it's a nice little thing that Kateki put into an item in the Welding Journal, American Welding Journal. So the lesson, don't do untreated, don't do arc strikes. And if there is an arc strike, treat it, get rid of it, gouge it out and repair it. For the same reason, don't go doing autogenous welding on duplex stainless steels. So phase balance, it's got to be good. If you get too high ferrite, you'll get low ductility, you'll lose corrosion resistance, and you'll get hydrogen cracking susceptibility. If you've got too much austenite, low stress corrosion cracking resistance and lower strength. And the problem is you're trying to balance the slow cooling, fast cooling, and in the middle you get intermetallics. And that's just making sure that you keep your heat down. So the composition, high nickel, high nitrogen increases the austenite, low heat input will give you excess ferrite. And if your cooling rates very slow, you get too much austenite. And if it's too fast, you get too much ferrite. Have you ever thought that you're walking along a tightrope here? It's really quite tricky. But welders do it all the time. So the higher the chromium and moly content, the worse the intermetallic phases. The nitrogen slows it, I've said that earlier. And the earlier duplex had no intentional nitrogen, and so they were very prone to both high ferrite and the intermetallic phases. So let's measure the ferrite. How do we do it? There are 3 ways. First way, you're not actually measuring it. All you're doing is calculating. And the people who do castings know all about this. They do a sum, they put all the levels of material in it, and they come out, yes, we're about the right level. It's absolutely no good for real welds because you've got mixing of the consumables, you've got the gas shielding composition, no good. So we have to do some measurements. All right, so cut out some samples. It's destructive, so you can't do it on site. Well, all right, let's keep going. Polish it smooth, 1000 grit and diamond, etch it, and it's usually electrolytic. The older, some of us old people used Murakami, and I always found trouble with that, but still the electrolytics work very well. And you get nice contrasting phases, and examine it at high enough magnification so you can separate out the features you're interested in. Then you count sufficient fields to obtain the accuracy that you want. And you do it either manually, that's ASTM 562, and boy, that's boring, it really is. Or by image analysis, which means you've got to have really good polishing, really good etching, and really good contrast. The number you get out at the end is a percent ferrite in the range 0 to 100. And it's the only method you can use if you're looking at a zone like heat affected zone. But yeah, the issues to consider that are that the polishing and etching is pretty specialist, and deciding on the accuracy, 33%, 10% or 5%, that's 33% is sort of waving around and saying, oh, I think it'll be about that. But all right, well, people do that. But it does require assumptions about the percentage of the phase that's there and the grid pattern that you're going to use. And all of that's set out in nauseating detail in 526. And you should realize that if the austenite phase is very heavily cold worked, then that may have generated martensite, which might overestimate the ferrite. If there are third phases or poor polishing, then your errors get worse. Interestingly, the standard actually recommends that you use a magnification of at least 400, but that may mean that the heat affected zone is a bit too narrow to be able to use that, because you really can't go measuring the ferrite in heat affected zone and weld and parent material and expect that they'll all be the same, because they won't. And here's an example. This is the parent material, here is the heat affected zone, and here is the actual weld. And imagine trying to do measurements on those at the same level, because one of the things that you've got to make sure of is that don't have too many of your measurement points are in blank. Okay, so there are tables. This is out of the standard, and I've picked out a few just to indicate how labour intensive it is. If you're aiming for 10% accuracy on a 5% volume fraction and you're using 25 grid points, you have to do 320 fields. I defy you to do that without going absolutely bananas. It's bad enough when you've got to do 15 and 5 or 40 or 10, but that's the statistics. All this is out of that. Here's the grids. You can have either a circular one or that, and you can pick however many numbers you want. But if you do a lot of them, then you get better accuracy. You may have to rotate the grid just to avoid any sort of periodicity, but it's definitely not designed for small percentages of third phases. It's designed really for looking at, are you at 30 or 40 or 50 or 60%? Because by the time you get down to this, then the work gets ridiculous. The alternative is to use a ferrotoscope. There are units actually which are designed specifically for measuring welds. The initial ones were a bit big. They're still moderately big, but they give a calibrated ferrite number. Note, ferrite number is not the same as ferrite percent. Talk about that in the next slide. Used by the Welding Research Council 1992 graph for designing consumables. Samples quite a small region around them for magnetic response, but it is not as small as a heat affected zone. There's the magnoscope. Basically, you hold a magnet against it and pull it off and look at the force, and that gives you a number, but it is recognized. Or the 7 magnetic pull-off gauge, which is really dinky. You put a little tab in it and see if it lifts off, and if it does, then you go for the smaller one and just keep going between them. And you get a number that is between 2 ferrite levels, used for small levels of ferromagnetism. And this is what we've got. This is the 1992 WRC, and these are ferrite numbers. And if you want some conversions, well, ferrite number 100 down here is 65% ferrite, approximately. Ferrite number 16, which is up here, is about 13.8% ferrite. And up to about 8 ferrite number, ferrite percent and ferrite number are about the same. So that's right over this side, right in the edge of the ferrite austenite, just before you get to the austenite ferrite. And there is a difference to this from the Schaeffler-DeLong, because you'll note that silicon's not down there. So why would welds fail? This is basically the standard things that all stainless steels might fail from, and I'm not going to go through them in any detail. There was talks about it before. The major extra issue with duplex is the sensitivity for heat input and what that does to the phases. Here we're talking about this level of nickel, usually, and so it's not as great penetration as mild steel or as the low-level ferritics, and it's not as bad penetration as the high nickels. It's somewhere in the middle. But you still got enough so the weld pool is more viscous than it is for the mild steel or the 12 chrome. And increasing the heat, increasing the current input won't improve the flow, but it may cause distortion or excess time in the sensitization, or giving you bad phases. Design of the joint, I'm sorry for the fiddling in the middle, but that's carbon steel roughly. And if this worked, yep, and that's roughly what you should do with the duplex. And it's as crude as you can be, but bigger gap there, less there, and more open because it's more viscous. And if you want to know more about that, then the practical guidelines for the fabrication of duplex stainless steels is available either from IMOA or from Nickel Institute. Surface coloration, much the same as for austenitics, 50 parts per million oxygen, light straw color, and that's what's set by AWS D18.1 2009. Actually, there's a later version of that now, which I'm having trouble downloading. But it's levels 1 to 3, and everybody agrees on that, and the Sandvik people did a lot, and other people did a lot of work showing that while that was done for hygienic purposes, for corrosion purposes, it's also a good number. And you can do it. This is hand welding of a super duplex piece of pipe with 22.7 parts per million of oxygen, and it's a good, clean weld. Unlike this, which is a bit of a mess, because we've got lots and lots of heat tint on it, but okay, you pickle it and you get rid of it. If you wind up with that amount of heat tint on a duplex, then you're probably going to have phase problems as well, but okay, you can get rid of it by cleaning. And the inspection after welding, absolutely standard, the 100% visual scan, code work, dye penetrant for location of defects, structural components, you'll have radiography, all set by the code, and ultrasonics if you need to, and down to the bottom, heat tint removal, mechanical or chemical. And if you're going to do mechanical, then make sure that it's not rougher than it should be, because rough surfaces tend to be more corroded. And you can blast it, glass beads, abrasives, pickling. Love that hydrofluoric acid. Well, I don't actually, but still, it does a good job. And electric polishing. Electric cleaning using the carbon fiber brushes is something that really is used quite a bit now. The difficulty about it is that it's very, very operator dependent. And unfortunately, they tend to give it to the apprentice and they don't give him some training or her the training beforehand. And that's really necessary, but it does work reasonably well. And you may need to passivate if you've done either of these, because the surface may actually need to be cleaned up and perhaps taken any sulfide inclusions out. Unlikely with the duplexes, but still. And it gets better as you go down that list. Okay, so let's just do quick whiz. I'm sorry, I'm running close to time here. The most commonly known duplex, 31803 was what it was called, developed in the 1970s. And I came across it in UK when the oil and gas industry were using it for running pipelines under the North Sea. That was fun. And the 2205, the new one, which I'll talk about in a sec, this 2205 has got distinctly better pitting resistance than 316L, simply because it's got more goodies in it. The trouble was the stainless steel mill managers didn't want to put nitrogen in it. Goodness knows why, but they wanted to keep it down in the bottom end of the range. So where are we? Down here, 08 to 0.11 or 14, I think it was actually, was the limit. So they were going, yeah, in the right thing. But welding, you lose a bit of nitrogen, and so the ferrite-austenite ratios went funny and you got intermetallic phases. So about 1990s, the people realized, and so they said, right, let's chop off the top half of these ranges, both the chrome, the moly, and the nitrogen, and we'll give that a new alloy name, 32205, which is 2205 plus. I've never seen it written as 2205 plus, but that is not the same thing as that. And a lot of people say to you, oh yes, we've got 32205, and you look at the actual spec of what they've got, and you find that it's actually 31803 and it's in the bottom half. So it's not as good. It's a bit harder to weld too. And it's a dual grade. Actually, sorry, there is one good thing, because a lot of codes talk about 31803 and don't talk about 32205. And so it's dual certified automatically. There are these families, and look at the variation going down here. We're increasing, well, generally increasing the chrome. The nickel, very, very low there because it's nice and cheap. And then we're getting more and more nickel up here because the chrome is actually trying to drive it to be all ferritic. And if you start adding moly, then it gets even worse, because that and that is going to try and make everything ferritic. And so you add nitrogen. And sometimes you've got to add some manganese, because as I said right back at the beginning, manganese helps you dissolve more nitrogen. So you've cut down on your nickel, so that's not helping, and you need that. And the same thing here, 0.5%. That's a lot of nitrogen. And this stuff, you can get it in, I'll talk about what you get it in, seamless plate, seamless tube and so on. You don't get it in plate. It's a bit hard to weld. So looking at the low alloys one, The 2304, or this is a proprietary grade, lower strength than the other duplexes, which is nice if you've got to do really severe forming. Less potential complications for the welding because you've got not a lot of moly in it and not big heaps of chromium, and PREs in the moderate range. Heat exchanger tubes, rebar, water, chemical industry, and this bridge. Lean alloy. This is from Gary, lean and mean. High strength, lower cost, decent corrosion resistance. Well, what's the parens? They're going from mid-20s into low 30s, round about the 30 mark, and there's lots of them, 2202. Most of these are proprietary. Common use in tanks, pressure vessels, structural applications. And the standard duplex. And this is two non-chemical, basically architectural views. This is duplex rods here, not painted carbon steel because you wouldn't want to do it. And it's not 316 because you'd have to have bigger 316. So it's very strong. That's the reason. This, well, actually, lots of it is bolted together because imagine trying to weld all these things together. But it works only because it's got good corrosion resistance next to the sea. I mean, that's the ocean. This is Singapore. Jörg would recognize it. And it's a tropical marine environment. So heat exchanger tubes, yep, you get lots of chlorides often. Rebar, because it's strong. Chemical industry because of the corrosion resistance. Structural applications, which are what these are. Oil and gas, and there's big, big heaps. Desal, not the really nasty high-level stuff, because you've got to go up to super for that. Pulp and paper, and that's probably the first of the industries back in the, well, it must have been in the 80s, where they were using it for digesters and piping systems. Lots and lots of pipe. Super duplex, the Sandvik one and the rolled alloys one. More corrosion resistant, 6% moly, so that gives its own problems in welding, and offshore, and it's more difficult to fabricate. The other super duplexes, really, there's a hell of a lot of them. There you are. And okay, let's look what's happening here. Bit of copper because you are interested in perhaps resistance against acid. Tungsten just for the corrosion resistance. And then moly, reasonable amount of it. Nickel to keep it as a duplex. 25 because it's a 2507. And the parens are all up here. Now note, here we've got 3 parens. This is minimum paren, is below 40. So technically, and technically with 2205, it won't cope with seawater at ambient temperatures, whereas these do. And quite a few of the specs nowadays, the ASTM, have a column saying PRE to be greater than 41 or greater than 42 or such and like. And then the hyperduplexes. There's only one producer, 2 grades, and it comes as seamless tube or sheet strip. And that's for reasons of, well, I haven't been told this, but it'll be for reasons of actually heat treatment and so on. And parens of 49 and 50, so it's really there. A bit of cobalt added there, interestingly, instead of nickel. Strengths, righto, so compare it with 316, this is a dual spec, and 515 minimum tensile, minimum elongation 40. And we've got at least double. And then we get up to the low, the alloy, the super, and the hyper, really, really strong. And the minimum tensile strength, this is the thing that's going to determine whether it stretches or not. And this is when it'll break, hopefully not. And the 789 is for this seamless tube. Service temperatures. It's going to embrittle if it gets to high temperatures. Many codes restrict it, but mainly because of the alpha prime. ASME allows 315. Europe goes down to 270, 240 for welded constructions, which is really, really thin. You saw the picture before of duplex embrittling at low temperatures. ASME code, lack of brittleness for use below -29 for all, for work below -29 for all product forms, except for thin forms. And I'm not going to go into the metallurgy of that. Properly produced, normally you can go down to -40, and you saw the example before. Oh, I've repeated it. Okay. I forgot I'd copied it. 2707, and they're all get down comfortably. Upper temperature limits, 315, 300, 250. And again, I repeated that. Sorry, I thought it was in another place and I meant to just take it. Castings, A890 duplex castings, 8 alloys, and 3 different names. Drives you mad. The ACI, American Casting Institute, the ASTM name, and the UNS number. Except it's very, very rare that people use the UNS number. 955, duplex for pressure containing parts, 7 alloys, same naming conventions, but it's pressure containing parts, so it requires solution annealing after major weld repairs, just to make sure that the hardness is okay and the microstructure is okay. And for testing for quality, this is not just for welded materials, this is for stuff actually arriving. The ASTM 1084 is for decremental phases in the lean duplexes, and this is for the ordinary ones, 923. And this was the one that came out first, and they started using it on the lean duplexes and they fell apart. And they realized this is stupid. Why would you use a really serious G48 test when we're not looking for it? All of them have been wrapped up in this ISO standard, which tests quality control of the microstructure, which is what those two do. And also it looks at the ferritic austenitic duplex balance. These don't. These apply only to mill-produced products, not fabricated. They only detect the intermetallic phases. They don't check for the ferrite-austenite ratio. You're meant to do it separately. There are 3 test methods. Either you do an etched micro and compare it with photographs, you do impact testing, -40 and 23, and you do corrosion testing, different temperatures, and I'm not going to go into those, but it's basically reflecting what happens. Interestingly, the duplex ordinary 2205, there's different temperatures for welded material and for parent material, which I suppose is sensible. Okay, so the petroleum one does the lot. It does the ferrite austenite, does the detection of detrimental phases, and it looks at the weld metal too, testing on welded material. And Norsoc, the Norwegian offshore, they did a good job on that. They got together and they said, hey, listen, we've got an oil industry. Let's have a set of standards that's going to work. And it's just been adopted by everybody else because it really did work. But you really it's very important that not only the fabricators, but also the welding people understand about the details of what you're testing for. It's a problem. You can't be welded and fabricated just like austenitic stainless steel. They are different, mainly because there's much more sensitive to bad fabrication. So it's really important the welding engineer, probably he's not in the shop all that often, but also the welders and the shop floor workers know what's going on. There is a minimum heat input for the duplex stainless steels, not just a maximum, and that's so that you don't wind up with nitrides. Typically, it's about 0.5 or 2.5 kilojoules per millimetre max, in that range. No autogenous welds, I've said that already. Bigger and larger tack welds for the duplex because it's stronger, and more testing, test and test. Last couple of slides. You can weld them with the same sort of processes, GTAW, TIG, MIG, etc. You can't use autogenous. That means you can't do resistance welding too. Joint design is similar, but not exactly the same. Generally, you need no preheat or post-weld. Well, that's the similar thing. Maximum heat input, and the value is going to depend on the alloy. Volts, amps over travel speed, yep. But you need to make allowance if you're using pulsed to avoid putting too much heat in. And there are matching filler metals. All of those are going to have a bit more nickel content than the base metal, because otherwise you've got a bit of a problem. You really need to make your weld the cathodic to the rest, so put a bit more nickel in. And you then take your heat tint off, preferably by pickling. And there's a maximum interpass temperature, although it's typically lower for the duplexes than for the austenitics. And that's it. Thank you. There may have been questions, but I didn't see them, so that's it.
There are about 23. and some in the
Three.
sky.
Okay. Well, how do you want to do it? Is somebody going to ask me the questions, or am I go and look at them, or what?
Dr. Krishnan, I think I'll get Dr. Krishnan to jump in and, you know.
Yeah,
Okay. Thank you.
So one question is on what is the effect of copper and tungsten in duplex and super duplex.
Tungsten isn't deleterious. Oh, sorry, tungsten. What's wrong with
Copper
tungsten?
and tungsten.
Yeah, it's actually tungsten comes off the thing. Tungsten is included as an improvement in the corrosion resistance, so it's not specifically that. Copper at the levels it's in there is basically to help avoiding getting. Yeah, look, I'm not 100% sure. How can I come back and tell people later?
Yeah, I think